last class we have studied about the approximate methods, and we know there are different approximate methods available to find the natural frequencies of the distributed and discrete mass systems. So, in case of distributed systems and discrete mass systems, we have seen the methods are Rayleigh method, Rayleigh-Ridge method, Galerkin method. Also one may apply for discrete system this matrix iteration method, and for discrete system also one may apply this Donkoly method to find the natural frequency if several masses are acting on a system. So, Holzer method and transfer matrix method also can be used. So, we have started with this Rayleigh method, and the Rayleigh principle is in a conservative system the frequency of vibration has a stationary value in the neighborhood of the natural modes. So, we have seen, so in the neighborhood of the natural modes the eigen frequencies are concentrated. So, in a conservative system the frequency of the vibration has a stationary value in the neighborhood of the natural mode. So, without taking the approximate, without taking the exact eigenvalue which is not known in most of the time, one may take an approximate vector and find the eigenvalues of the system. So, this is written by this Rayleigh quotient Rz. So, omega square, this is the approximate value. To find the approximate value we can take a approximate function z. So, by taking that function I can write this Rayleigh quotient equal to z transpose k z by z transpose m z, where k is the stiffness matrix, m is the mass matrix of the system. So, this is for a discrete system you can write, and this z can be taken in such way that this z transpose m z can be unity matrix and this z transpose k z can be a diagonalized matrix. So, by taking that way, so one can write this R z, that is this Rayleigh quotient equal to, so I can write this z as the summation of a vector. So, this is equal to, I can write this is summation of C I Z I. So, this Z I is a matrix, this is a diagonal matrix, and I can write this R z equal to C transpose Z transpose K Z C by C transpose Z transpose M Z C. So, the Z are calculated in such way that this Z transpose M Z can be unity matrix and this Z transpose K Z be a diagonal matrix written by P. So, that way if you write, so this becomes C transpose P C by C transpose I into C. So, this P is a diagonal matrix which contain the eigenvector or the approximate eigenvector in the diagonal. So, it will be C I omega I square, I equal to 1 to n C I square omega I square by summation C I square. So, by using this formula, so you can find. So, let us write for the first mode. So, R1z can be written as C I square omega I square by C I square. So, it can be taken C1 square plus omega 1 square plus C2 square plus omega 2 square by writing this as omega. So, this can be written in this form, this is equal to omega 1 square plus 1 plus summation I equal to 2 to infinity epsilon square omega I square by omega 1 square by 1 plus epsilon square, where epsilon is the C I by C R. So, here we are assuming that the rth mode has a variation from the phi I. So, the exact eigen value is phi I, but we are taking this as Z R. So, that there is a variation in this phi. So, let the variation, due to this variation the C R will be large. So, the C I by C R for all the modes except R equal to I will be very small, and that thing can be taken as a small parameter epsilon which is very less than 1. So, epsilon equal to very less than 1. So, this R1z one can find, this is equal to omega 1 square plus 1 plus this term. So this is the additional term, or one can tell that this will give omega 1 square plus some term in the decimal term. So if you take an error in 10% in the, so it can be shown that if you take error in 10% in the eigenvector, then there will be a 1% error, because it is epsilon square, error will be in the order of epsilon square. So it will be 1% error in the eigenvalue. So we have, so using this thing we can solve many problems, or we can find the eigenvalues, or we can find the natural frequency of different systems. So let us consider this system. So this is a cantilever beam, and at the end there is a attached mass. So let us find the frequency of the system. So in this case we can assume the solution to be in this form, that is equal to yx into cos omega t, and you know that its deflection will be, so as this end is fixed, so the slope will be 0 and the deflection may takes place like this. So this is the deflection of the system. So you can assume this deflection in this form, yx equal to a into 1 minus cos pi x by 21, let us assume. So by assuming this thing, so if you put this x equal to 0, you can find this yx equal to 0. Also if you differentiate this thing, then it will becomes, you can find that the y dash x also equal to 0 at x equal to 0. So we satisfy this left hand boundary condition, that is it will have a slope 0 and displacement 0. So by taking this function y x t equal to yx cos omega t, where yx equal to a into 1 minus cos pi x by 21. So we can find the natural frequency of the system. Already from the exact solution you can find the equation, you can find the frequency equation and the mode shape from this equation. So by solving this Euler-Bernoulli equation you can find, so there you can take this phi x equal to c1 sin hyperbolic beta x plus c2 cos hyperbolic beta x plus c3 sin beta x plus c4 cos hyperbolic c4 cos beta x. So this is the generalized mode shape. So in this generalized mode shape, if you put the boundary conditions, so the boundary conditions are at the left end, phi x will be equal to 0 and phi dash x will be equal to 0, that is the displacement equal to 0 and slope equal to 0, and in the right end this bending moment will be equal to 0 and the shear force will be equal to, the shear force will be equal to the inertia force of this system. So as you have added a mass, so let this is m, so for this mass, so this will be inertia force will be my double dot. So this my double dot will be equal to the shear force. So shear force equal to ei del q y by del x q. So by taking this generalized phi equation, mode shape equation, and substituting this boundary condition, you can find the exact frequency function and the mode shape. So in that case you may have to go for the computational method to find the frequencies of the system, as the frequency equation will not be a simple equation, you have to go for the computation numerical methods. But we can assume in this approximate method, we can assume the solution yx equal to in this form, yx equal to a cos pi x by 21. So y dot x t can be written in this form minus omega yx sin omega t equal to minus omega a 1 minus cos pi x by 21 sin omega t. So the kinetic energy of the system, it will contain two parts, one due to this beam and other due to this mass. So kinetic energy due to this beam part will be equal to half m y dot square dx, and due to this mass you can also find. So this due to this beam let us find first. So, y dot expression, by substituting this y dot expression in this integral. So, you can write it equal to 0 to L half m omega square 1 minus cos pi x by 21 square a square dx. So, then you can find this equal to m a square omega square by 2 0 to L 1 minus cos pi x by 2 L into 2 L square dx. So, here it is taken y x equal to a 1 minus cos 2 pi 1 minus cos pi x by 2 L. So, this is 2 L, and so this can be written m a square omega square by 2 into 0 to L 1 minus cos pi x by 2 L square dx. So, this is equal to m a square omega square by 2. By integrating this thing, you can find it equal to m a square omega square by 2 3 by 2 L minus 4 L by pi. So, this is equal to m a square omega square L into 3 by 4 minus 2 by pi. So, this is the maximum kinetic energy obtained due to the beam vibration. Similarly, we can find the maximum kinetic energy at the tip of the mass. So, at the tip of the mass, we have to find the velocity, and half into mass into velocity square will give you the kinetic energy at this tip, and we can find the maximum kinetic energy. So, which is given by this equal to half m omega a square, as the velocity, maximum velocity will be maximum velocity at this end. So, this is the expression for the velocity. So, maximum velocity at the end will be equal to a omega. So, this part will be equal to 1. So, maximum velocity will be equal to a omega. So, you can write the maximum kinetic energy of this mass will be equal to half m omega square a square, where m is the mass, tip mass. So, m is the tip mass. So, maximum kinetic energy of the tip mass already you have obtained, and this is the maximum kinetic energy of the beam. So, by adding these two, we can find the total energy, kinetic energy of the system. So, total kinetic energy of the system equal to m a square omega square L 3 by 4 minus 2 by pi plus half m omega square a square. Similarly, we can find the potential energy and the maximum potential energy. Potential energy expression can be given by half E I 0 to L d square y by dx square dx. So, this integration you can do by taking this y equal to. So, already the function y is given to us, or known, we have assumed this function a into 1 minus cos pi x by 2 L. So, by assuming that function, I can find this potential energy equal to half E I 0 to L del square y by del x square into dx. So, the maximum value will be equal to pi 4th by 64 E I by L q a square. So, now by equating this maximum kinetic energy with this maximum potential energy, you can find omega square equal to. So, omega square equal to, you can find this is equal to 3.0382 E I by m plus 0.232 m L into L cube. So, this is the expression for the cantilever beam with an end mass. So, if the end mass is not there, or due to the end mass, this is the additional term, you may observe that this is the additional term due to the end mass, or this is the additional term due to the mass of the beam. So, we have considered the mass of the beam. So, this is the additional term. If you can find, or you can do it in this way. So, if you have only a mass at the end and this beam is massless, then by considering this weight equal to mg. So, the deflection here I can find equal to, this is W equal to mg, this is the weight acting at this end. So, the deflection equal to at the end equal to W L q by 3 I. So, the deflection at the end equal to W L q by 3 I. So, the stiffness of this beam can be written as W by delta. So W by delta will give me 3 EI by LQ. So this is the deflex, or this is the stiffness of the beam or the system. So from this deflection and from the mass, tip mass, so this is the tip mass m. So the natural frequency omega square will be equal to root over k by m. So root over k by m will give 3 EI by LQ by m. So this omega square you can write. So omega square will be equal to k by m. So this k equal to, already we obtained, this is equal to 3 EI by L cube. So this is 3 EI by L cube and m equal to m. So this becomes 3 EI by m L cube. So this is 3 EI by m L cube. So this is the, or the frequency equal to root over k by m. So this becomes 3 EI by m L cube. And when you are taking into account the mass of the beam, so here we have considered the mass of the beam. So when you are taking the mass of the beam, then we are getting this frequency equal to root over, so this I can take it equal to 3. So this is equal to 3 EI by m plus, so you have derived it. So this is 3 EI by m plus 0.232 ml. ml into L cube, where this ml is the total mass of the beam, m is mass per unit length of the beam. So by taking into mass of the beam into account, this expression for the cantilever beam with a tip mass is reduced to this form. So this is now the frequency of this cantilever beam with end mass becomes 3 EI by m plus 0.232 ml into L cube when we are taking the mass of the beam into account, and this is equal to root over 3 EI by m L cube when the mass of the beam is not considered. Similarly, we can find for the simpler case of a spring mass system. So this is spring with stiffness k and this is mass m. So let us consider the mass of the spring. So if you consider the mass of the spring, so without considering the mass of the spring, we have obtained the kinetic, we have obtained the frequency equal to omega square equal to k by m. So now considering the mass of the spring, we can find also the natural frequency of the system. So this system is also similar to this system. This is the longitudinal vibration of a rod and with an end mass. So by taking this system, so these two systems are also equivalent. So let us consider the mass of the spring, or in this case the rod. So in this case let us take at a distance x from this fixed end. So let us take a small element here, or in this case in the spring also we can take a small element. So the small element dx, let us take a small element dx at a distance x and let mass per unit length equal to m. So mass per unit length equal to m. So mass of this element equal to m dx. So mass of this element equal to m dx. Let u be the deflection at this point. So if u is the deflection at a distance x, so I can write this u equal to, so this u can be written as the, so if the displacement here equal to ui or ul at this tip, so I can write this u at any distance will be equal to x by L. So this is equal to x by L into ui. ul, let me write equal to ul. So ul is the displacement at this distance x, distance L or at the tip. So this u at any point will be equal to ul by L into x. So this is u. So I can write this u dot to find the kinetic energy. I can write this u dot equal to, so I can write this is equal to u L dot. Similarly, I can write this mass of this element equal to, mass of this element will be equal to, let m is the total mass of this rod or mass of the spring. So in that case it will be m by L into dx. So this is the mass of the elemental mass. So the elemental mass equal to m by L into dx, where m is the total mass of this, mass of the spring, or in this case the mass of the rod, mass of the spring, or the case of, in this case it is the mass of the rod. So the kinetic energy I can write equal to, so T is the kinetic energy, T equal to half. So this kinetic energy will be due to two components, one due to the spring, mass of the spring, and other due to the tip mass, or in this case it will be due to this rod, and in this case it is due to this mass. So you have to add these two, or here you have to add for these two effect. So taking these two kinetic energy, so it can be written as half. So tip mass I am writing is small m, so u L dot square. So this is the kinetic energy for the tip mass, plus for this elemental mass I can write, and I can find for the whole beam. So it will be 0 to L u dot square dm. So this thing can be written as half m u L dot square plus half m by L 0 to L x square by L square u L dot square dx. So we can write it equal to half m. So this u dot already we have taken equal to x by L u L dot. So u dot I can write x by L u L dot. So this becomes m u L dot square plus half m by L, and this will be u L dot square, I can take it out. So this will becomes integration 0 to L, and this is L into L square. So this become L cube. So this becomes 0 to L x square dx. So this integration will become x cube by 3. So by substituting 0 to L, so it will be x L cube by 3. So I can add these two terms. So by adding these two, you can write this is equal to, this is m plus m by 3 into u L dot square. So this is the maximum kinetic energy, this is the maximum kinetic energy of the system. Similarly, the potential energy can be written in this form. So potential energy V equal to half k u I or u L square. U L is the maximum displacement. So the maximum potential energy equal to half k into u L square. So let us take this u1 equal to a, or u with time I can take it equal to a cos omega t, a cos omega t. So this ut max maximum, ul maximum will be equal to, so the maximum value will be equal to a. Similarly, the maximum velocity ul dot maximum will be equal to, so this will be a sin omega, a omega sin omega t. So the maximum value will be equal to omega a. So here we are assuming the time function in this way. So ul equal to a cos omega t. So ul will be maximum value will be equal to a, and UL dot maximum value will be equal to omega A. So, by substituting these terms in this potential energy and kinetic energy, so T max maximum kinetic energy will be equal to, so maximum kinetic energy equal to half m plus, so there we got capital M by 3 omega square A square, this is equal to half k A square, this is the maximum potential energy and this is the maximum kinetic energy. So, this is equal to V max. So, by equating these two I can write this omega square equal to, so this will be equal to k by m plus m by 3. So, omega square equal to k by m plus m by 3. So, by taking into account the mass of the spring in the natural frequency, one should take this factor into account, that is m by 3. So, by taking into account the mass of the spring, one may write this omega, that is the natural frequency of the system, equal to root over k by, this is m plus m by 3. So, where m is the mass of the tip mass. So, m, so this is the spring mass system. So, in the spring mass system, m is the mass of the mass at the tip and m, capital M, is the mass of the spring. So, if one consider the mass of the spring, then he has to modify the equation for the system without, when we are not considering the mass of the spring. So, this is without considering the mass of the spring and this is considering the mass of the spring. So, when mass of the spring is considered, so one has to take, or one has to add 1/3 mass to the tip mass to find the frequency of the system. Similarly, in case of cantilever beam, so we have already derived that in case of the cantilever beam, if you consider the mass of the beam, then a factor of 0.232 to be added to the mass of the tip, mass at the tip. So, the effective mass, this can be considered as the effective mass of the system in that case. So, the effective mass of the system in, when you consider the mass of the beam, will be equal to m plus 0.232 mass of this beam. Similarly, in case of the spring, when we are considering the mass of the spring, then it will become 1/3 of the mass of the spring. So, by considering 1/3 of the mass of the spring, you can find the natural frequency of the spring mass system without considering the mass of the spring. So, when you are not considering the mass of the spring, then this is equal to root over k by m, and when you are considering the mass of the spring, just add 1/3 of the mass of the spring to this mass, tip mass, and you can find the frequency of the system. So, in this way you can apply this Rayleigh method to find the natural frequency of different systems. Let us consider another example. So, in this example we will take a torsional system. So, in this torsional system, so let this is a shaft. So, in this shaft let there are 3, so let us consider 3 discs mounted on the shaft. So, there are 3 discs mounted on the shaft. This is disc 1, this is disc 2 and this is disc 3. So, let us consider the inertia of these are same, that is j, and this rotation I can write equal to theta 1. So, let us write this as theta. Okay. So, we can write this as theta 3. So, this is theta 2 and so this is, or let me start from this end. So, this will be, in this case it will be equal to theta 3, this is theta 2 and this is theta 1. So, this is 1, system 1, this is 2 and this is the third mass we are considering. So, and the shaft, let us assume the shaft has equal stiffness in this 3 range, this is k, the shaft stiffness, and the rotors are mounted at equal distance. So, this is L, this is also L, and this is also L. So, in this case we want to find the natural frequency of the system. So, already you know this K, the stiffness of the system can be written from this formula T by J equal to C theta by L or G theta by L or T by IP. So, polar moment of inertia of the shaft. So, where IP is the polar moment of inertia of the shaft and T is the applied torque and G is the rigidity modulus and theta is the rotation and L is the length of the shaft. So, in case of continuous system you have solved similar problems by considering the wave equation. So, for a fixed shaft you have found. So, in that case fixed shaft and shaft with one end fixed also you have found, and you in that case you have found by using this wave equation. So, solving this wave equation you have found the frequency of that case. So, in this case by taking this approximate method, or now we will assume that we will assume the mode shapes of the system and we will find the natural frequency of the system. So, if we are interested for finding only the fundamental frequency, we can proceed in this way. So, we can assume that when the rotation of this or this rotation theta 1, theta 2, theta 3 will be proportionate to the applied torque, or it will be proportionate to the moment of inertia of these rotors. So, now let us find the kinetic energy of the system. So, this kinetic energy T will be equal to half J theta 1 dot square plus half J theta 2 dot square plus half J theta 3 dot square. So, this thing can be written equal to, as we are considering same J for all the three. So, it can be written half J into theta dot square plus theta 2 dot square plus theta 3 dot square. So, this is the kinetic energy of the system and the potential energy of the system. To find it, so we should know what is the rotation of each segment. So, in the segment 1, so it is rotating with theta 1, but this between in segment 2 the shaft will be rotated this side left side by theta 1 and right side by theta 2. Similarly, in case of this segment the left side is rotated by theta 2 and the right side is by theta 3. So, there will be relative motion theta 2 minus theta 3 in this case and theta 3 minus theta 2 in this position. So, the potential energy can be written as this potential energy V will be equal to half K theta 1 square plus half K. So, for this portion I can write it equal to theta 2 minus theta 1 square, and for this portion I will write this equal to half K theta 3 minus theta 2 square. So, now I can assume, so as I do not know the exact modal function, so I can assume this thing. So, I can assume that this theta 1 equal to A cos omega t or A1 cos omega t, and theta 2 equal to A2 cos omega t, and theta 3 equal to A3 cos omega t. So, by assuming this thing I can write the maximum kinetic energy. So, T max. So, T max will be equal to half J omega square. So, this is the expression for kinetic energy. So, this becomes half J theta 1 dot square, theta 2 dot square plus theta 3 dot square. So, maximum will be A1 omega square, A2 omega 2 square and A3 omega square. So, I can write this equal to, so half J omega square. So, A1 square plus A2 square plus A3 square. Similarly, V max, that is this potential energy of the system. So, this is the expression for V potential energy. Here by substituting this maximum theta will be equal to theta 1 will be equal to A1, theta 2 will be equal to A2 and theta 3 will be equal to A3. So, by substituting this thing So I can write this equal to half. So this will be equal to half k. So I can take this k common. So this will become, so a1 square plus a2 minus a1 square plus a3 minus a1 square. So in this case we can assume this a1, a2, a3 in this ratio. So I can assume this a1 equal to 1 and a2 equal to 2 and a3 equal to 3. So I can assume in this case, in this rotor, so when it is rotating, this is rotating 1. So you know this free end will have more rotation than this, and this will have the least rotation. So I can assume this rotation to be equal to 1. So here it is equal to 2 and the rotation of this one equal to 3 units. So by taking this thing I can write, so I can write this expression omega square, or I can write this T max equal to V max. So maximum kinetic energy equal to maximum potential energy. So by equating that thing, so I can write this half j omega square. So half j omega square into a1 square plus a2 square plus a3 square into omega square equal to half k into a1 square plus a2 minus a1 square plus a3 minus a1 square. So this omega square will be equal to, so I can divide, so this half will get cancelled. So it will be equal to k into a1 square plus a2 minus a1 square plus a3 minus a1 square by a1 square plus a2 square plus a3 square into j. So by taking this a1 equal to 1, a2 equal to 2 and a3 equal to 3, so it will be equal to 1 plus, so this becomes 1, so 1 plus 1 2, and here we have a3 minus a1 equal to 2, so square will be equal to 4, so 4 plus 1, so this becomes 6. So and in the here you will have, so this will becomes the upper side becomes 6k, and here you have 1 plus 4 plus 9, so 9 plus 4 13 plus 1, so you have 14. So you will have this thing equal to 6 by 14. So 6 by 14 becomes, so you can find 6 by 14, so this will becomes 0.428. So you can write this equal to, so omega square equal to 0.428 k by j. So we can find this omega, so it will be equal to root over 0.428. So this becomes 0.654 root over k by j. So let us calculate it again. So this becomes 1 and then this is 1, so 1 plus 1 2, and here this is a3 minus a1, this is 2, so 2 square 4, so 4 plus 1, this is 5 plus 1 6, and here it is 1 plus this 4 plus 9, so 13 plus 1 14, and here equal to 6, so 6 by 14, so 6 by 14 equal to 0.428 and root over that equal to 0.654 root over k by j. So in this way you can find the natural frequency, or this is the fundamental frequency, of the system. So you can find the fundamental frequency by using this Rayleigh method. So for a lumped parameter system also you can find the fundamental frequency. let us have a shaft. It is supported like this and you have several masses attached to this shaft. So, in this case you can find the natural frequency of the system. So, by equating the maximum kinetic energy of the system to the maximum potential energy of the system, you can find the natural frequency. So, let us assume that under this mass 1, 2 and 3, or let you have n mass. So, this n mass, so if you have n mass, then the elastic deflection. So, let this is the elastic line of the system. So, in this case I can take, let under this mass m1, let the displacement is y1. So, this displacement is y1. Similarly, under this mass 2, so let the displacement is y2, and under this yn, so let this is the nth mass placed here. So, in this case of nth mass, let it will be yn. So, let these are the displacement under each mass. So, we can find this maximum potential energy of the system will be equal to, so maximum potential energy will be equal to mgh. So, I can write this maximum potential energy equal to, so as this displacement will takes place from 0 to this value gradually. So, I can take this equal to half. So, it can be taken equal to, so the maximum, I can find the maximum potential energy of the system. So, by finding this maximum potential energy, I can write this equal to, as it will takes place from 0 to y1, I can write this equal to w1 y1 plus half w2 y2 and similarly half wn yn. So, where w equal to mass into gravity. So, this can be written equal to g by 2 into summation m into y. So, this is the maximum potential energy, or y will be equal to y max. I can take, similarly I can find the maximum kinetic energy. So, the maximum kinetic energy term, maximum kinetic energy can be given by this. So, maximum kinetic energy will be equal to half m1 v1 square plus half m2 v2 square. So, plus half mn vn square. So, this v equal to, so as I am assuming this y in the form of a cos omega t or a sin omega t. So, the maximum value will be equal to a omega. So, it will be equal to, or vn will be equal to omega yn. So, substituting this in this equation, you can write this T max equal to, so T max will be equal to half m1 into omega y1 square plus half m2 into omega y2 square, and in this way you can write it is equal to half mn. I am writing this as capital M. So, this is capital M, and this will be equal to half mn yn into omega square. So, this is the maximum kinetic energy, and already you got the expression for the maximum potential energy. So, by equating this maximum kinetic energy with maximum potential energy, so you can write the expression, or you can find the expression for this omega n. So, omega n square will be equal to, so by equating this you can write this expression, this kinetic energy expression as half. So, I can write this maximum kinetic energy as half omega square into summation m y square. So, now dividing this, I can write this expression, or I can write this half g by 2 summation m y will be equal to half omega square summation m y square. So, I can write this omega square equal to summation m y by summation m y square. So, omega square, that is the frequency square of the natural frequency, can be obtained in this way as g into, this is g is the acceleration due to gravity, into summation of the mass at each position. You know the mass at each position, and if you know the displacement, corresponding displacement, so the frequency square can be obtained, or the frequency can be obtained by equating the maximum kinetic energy with potential energy, and the expression can be given by this, or this omega n will be equal to root over g summation m y by summation m y square. So, in this way, when a lumped mass system is there, you may find the natural frequency of the system. So, let us consider let us go to the other types of approximate method, and now let us study about this matrix iteration method. Matrix iteration method is used for this multi degrees of freedom system. In case of multi degrees of freedom, let us consider a multi degree of freedom with n number of degrees of freedom. So, in that case, you can write the equation motion of the system in this form: mx double dot plus kx equal to 0. So, this is the free vibration equation for this case of a multi degree of freedom system. So, if x you can write as the mode shape of the system, so you can write this equation also in this form by using this m inverse k as a. By writing a equal to m inverse k, I can write this equation in this form: x double dot will be equal to m inverse k x, or x double dot will be equal to a x. Now, by considering the normal mode vibration x equal to, I can take x equal to x e to the power I omega t. So, x equal to, I can take x e to the power I omega t. So, by taking e to the power I omega t or sin omega t, I can get this x double dot equal to minus omega square x. So, x double dot will be equal to minus omega square x. So, minus omega, this omega square I can take equal to lambda, or the eigenvalue of the system. So, this expression I can write in this way. So, it will be equal to a x equal to lambda x, or a x equal to lambda x, or in matrix and vector form if I write. So, this is a matrix into x vector will be equal to, a matrix into x vector will be equal to lambda into this x vector. So, you just note that using this dynamic matrix A and this normal mode or the mode shape of the system, you can observe that this mode shape repeats itself. So, when I am taking the mode shape of the system and it multiplying with the dynamic matrix, then this mode shape repeat itself. So, the normal mode when multiplied with the dynamic matrix will reproduce itself. From this equation we are observing that when this normal mode is multiplied with this dynamics matrix, it is repeating itself. So, this is the basis of this matrix iteration method. So, if we start with an assumed value of this x and go on iterating by knowing this dynamics matrix A, so we can find some value of x which will satisfy this equation. So, that value will be the normal mode of the system. So, taking that normal mode of the system, we can find this value, the eigenvalue lambda of the system. So, the steps you can follow to in this method. So first you find this dynamic matrix A. So dynamic matrix A can be found by M inverse K. So by finding this dynamic matrix and assuming one mode shape, so this mode shape X you can assume. So let for a 3 degree of freedom system you can assume the mode in this way. Let me write this is 1 2 3. So this is the assumed value I have taken. So by taking this thing, so I will multiply this assumed value with this dynamic matrix. So by multiplying this assumed value by this dynamic matrix I can get, so let this A will be a 3:3 matrix and this is 3:1. So this gives me a 3:1 vector. So in this 3:1 vector, so I can normalize that vector and I can find this normalized mode shape of the system. So I can find this normalized mode shape of the system, and after finding this normalized mode shape of the system, if it is equal to the previous or the assumed mode shape, then it will satisfy this equation A x equal to lambda x. So if it is satisfying this equation, then I can take this x value or the assumed value as the mode shape, and I can calculate this value of lambda from this expression. So to find the higher modes you can, so to obtain the higher mode, you know the any vibration can be written as this C1 x1 plus C2 x2 plus Cn xn. So where these x1 x2 xn are the normal mode vibration of the system, and x is the free vibration resulting free vibration of the system. So this x can be written as C1 x1 plus C2 x2 plus Cn xn. So this is the assumed mode we are taking for our calculation. So if this assumed mode contain this first mode, then the resulting vibration or the resulting natural frequency or eigenvalue what we want to obtain will leads to the fundamental frequency only. So to find the higher mode frequency, we have to make this C1 equal to 0 from this resulting vibration. So to make this C1 equal to 0, we may use this orthogonality principle. I can write this x equal to x1 bar, x2 bar and x3 bar. So these are the assumed mode, and this x1 x2 x3 or x1 x2 x3 are the eigenvalues of this or the values of the ith mode of the system. So x1 will be equal to this x1 will be equal to x1 x2 x3, and this x, that is the assumed value I am taking in this form, that is equal to x1 bar, x2 bar and x3 bar of the system. So applying this orthogonality principle, I can write this x1 so as this x equal to C1 x1 plus C2 x2 plus C3 x3 plus Cn xn. So applying this orthogonality principle, I can write x1 dash mx will be equal to x1 dash m C1 x1 plus C2 into x1 dash m x2 plus C3 into x1 dash m x3, and similarly I can write this is Cn x1 dash m xn. So from the orthogonality principle, you know x I m x j equal to 0 if I not equal to j. So when I not equal to j, so this becomes 0. So this is the orthogonality principle. So applying this principle, you can check that all these terms becomes equal to 0. So this x1 dash mx2 equal to 0, x1 dash mx3 equal to 0. Similarly, all these terms equal to 0, and you are left with x1 dash mx equal to x1 dash C1 into x1 dash m x1. So, as C1 to be equal to 0 to find for the higher modes. So, putting C1 equal to 0. So, you can find or you can write this left hand side should be equal to 0, that means x1 dash m x1. So, x1 dash m x will be equal to 0. So, this x1 dash you can write in this form, that is equal to x1 x2 x3, the transpose of x1 x2 x3 into, let me take a 3:3 3 degrees of freedom system, then it will be m1 0 0 0 m2 0 0 0 m3 into, this is x1 bar, x2 bar and this is x3 bar. So, if you multiply these things, so you are getting this is equal to m1 x1 x1 bar plus m2 x2 x2 bar plus m3 x3 x3 bar. So, this should be equal to 0. Okay, so I can write this x1 bar equal to minus m2 by, so x1 bar will be equal to minus m2 by m1 x2 by x1 into x2 bar, and this is equal to minus m3 by m1 into x3 by x1 into x3 bar. Or I can write this equal to x1 bar equal to minus m2 by m1 into x2 by x1 into x2 bar minus m3 by m1 into x3 by x1 into x3 bar. Now, I will write this x2 bar equal to x2 bar and this x3 bar equal to x3 bar. So, I can write this left side as x1 bar, x2 bar, x3 bar. So, this is the assumed mode I am taking now. So, this will be written as, so as this does not contain x1 bar. So, this will be 0 0 0 and this is equal to minus m2 by m1 into x2 minus x1 minus m3 by m1 x3 by x1. Similarly, this will become 1, this is 0, this is 0, this is 1, this into x1 bar, x2 bar, x3 bar. So, you can see, so in this case the fast mode is not present in the system. So, the fast mode we have eliminated by using this matrix. So, this matrix is known as the sweeping matrix. So, today class we have studied or we have taken some examples for the Rayleigh method and found the natural frequency of the systems. Also, we know the principles of matrix iteration and also we have found or we have studied the procedure for finding the frequencies for the higher mode in case of this matrix iteration method. So, next class we will complete this matrix iteration method and also we will study the Rayleigh method and Galerkin method and Donkoly method, which are the approximate methods for finding the natural frequency of a system.